Welcome back, everybody. This is Mr. Diamond. We are in section 2 of chapter 5, even though this year it's actually chapter 4 of senior physics, and we're going to be talking about energy. Specifically, though, we're going to talk about kinetic energy. First, though, with all the stuff out of the way relating energy, work, and power, we can get back to just focusing on what energy is. There are a lot of types of energy. There are things like mechanical energy that help like a frog jump or a car to move. Nuclear energy like fusion in the stars, fission inside of the Earth's core, and that was used for atom bombs. Chemical energy in the food that we eat that we convert into ATP, striking a match, doing a sort of chemical reaction that releases heat. Electrical energy that goes through power lines or lightning that's allowing me to power this computer. Electromagnetic energy that comes in the form of visible light, infrared radiation, radio waves, ultraviolet light, microwaves, all of that. Thermal energy from things melting or from heating up soup. You can change the thermal energy. All of those are a bunch of different categories of energy. But in general, we can split them into two categories: kinetic energy and potential energy. Kinetic energy comes from kinetikos. I believe that's the traditional pronunciation. Marina taught me that last year, our Italian exchange student, meaning motion. The energy associated with something moving, and then potential energy is the energy associated with position, configuration, or makeup of something. It's a relation to its surrounding. It's what potential does it have to do something. A bullet, if we use the example I talked about a little bit in a few videos ago, a bullet has kinetic energy after it's been shot. It's moving very, very quickly, and that's got a bunch of energy pent up into it that it can be transferred to you and cause you physical pain if you were to get hit by it. Potential energy, though, comes from something like a brick of uranium. There's a lot of potential for energy in that radiation that's inside of it, but we don't see it. It's not like a brick of uranium is just like vibrating and like bouncing up and down on the table. We don't see that. It's contained inside of it. Another example of potential energy we're going to talk about is like putting something up. Like, for example, if I take my phone, or if I take my pen, because that's safer, and I hold my pen up, there is the potential for energy to come out of this pen if I let it fall. So the higher up it is, the higher potential. Sorry, hit my little mic there. The higher potential that it has to have energy, or the higher amount of energy could be released from it based on its given position. We're going to start with kinetic energy. It's one of the most common equations that people have actually heard before this class, so a lot of you have already are familiar with it. It's Ke equals 1/2 mv squared. However, this equation actually comes from related work. Or relating the work, the kinematics, and the Newton's second law equations together. We actually combine all three of those together, and we get a Ke equals 1/2 mv squared. F equals ma is based on Newton's second law. Work is equal to force times distance, so we would get work equals ma times distance. And then we can rearrange and plug in our v2 equals v naught, or v squared equals v naught squared plus 2a x minus x naught. Combine those together, and then do a little bit of other work, and we can end up getting our kinetic energy equation. I'll show you what that looks like in class. It's not really worth it or to go into detail about it in this video here. Now, technically, our work energy theorem we looked at before mentioned that it was energy of motion, kinetic energy. So our actual accurate form of that final form, where we'll talk more a little bit about later, is that net work is going to be equal to the change in kinetic energy. If work is done, that means that energy was used, because we said they're all connected together, but more specifically for the definition of work, a force was done over a distance. If a force was done over a distance, that means something had to have moved, which means that there was kinetic energy. There was energy of motion involved in it. So an example that we can do without calculations is a question like this. A car is traveling at 60 kilometers an hour and has a stopping distance of 20.0 meters. If the car goes double that speed, what would you expect its stopping distance to be? Assume that the force needed to brake is not affected by speed. So if the force is not affected by, or if the force needed to brake is not affected by speed, the stopping distance was 20 meters. We're increasing the speed by a factor of 2. But, and if we go back to our equation for Ke equals 1/2 mv squared, notice that velocity in there is squared. So what we can do is we can assume, well, let's just pick a number. If it was like, let's say it says 60 kilometers an hour, we could plug that in and we could try to actually solve for it. But instead we know it's going to be double that. It's going to be 120. And if you square that, that means it's going to increase not by a factor of 2, but by a factor of 4 of the distance that it's going to take. So it would actually take 80 meters for it to stop in that case, because the kinetic energy that something has and that change in that kinetic energy is proportional to the square of the speed that it was traveling. Now, that's kind of a weird question to start with. I wanted to start with like a little bit of a tougher one, because we're going to try to do some more conceptual stuff. But we'll talk about that a little bit more in class, and this question should make a little bit more sense. I am going to upload it with this. I believe, maybe not. Who knows? The world's all sorts of weird. I do have some other examples. How much kinetic energy is contained in a 1,400 kilogram car traveling at 20 meters a second? What about at 30 meters per second? How much work would be done accelerating a 1,400 kilogram car from 20 meters a second to 30 meters a second? And I'll work out those examples in a separate video. Key ideas here, though. Kinetic energy is equal to the energy of motion. The change in kinetic energy, if we go back here, will tell you how much net work was done. That example problem I had, the second one, will make a little bit more sense when we work that one out in that associated video. But kinetic energy is our energy of motion, and it's kind of the easier of the two forms of energy we're going to talk about here. So that's what I've got for you in this video. If you have any questions, please send me an email. Otherwise, this is Mr. Diamond signing off. Have a good rest of your day, everybody.